All right, everyone, it's that time again. So here's the next installment of the Physics 328 video. I got myself some new tablet writing software, and it has absolutely changed my life. It's revolutionary. So I actually think it's going to make watching the videos a little more tolerable as well. So let's see how that goes. Today, what we're going to do is we're going to talk about a method of trying to find principal axes of a rigid body when you've picked some origin and you want to work with a rotational inertia tensor that's diagonal. Now, sometimes if the shape of the body is very simple, then you might be able to just guess or in some way deduce by being clever what the principal axis directions must be. But in general, it might be hard to do, and so we're going to try to develop a method for finding the principal axes, assuming that you have first discovered what the rotational inertia tensor looks like for some arbitrary axes that you selected. So maybe this tensor that you calculated has off-diagonal elements. So how could you go from that to something that would tell you what the diagonal elements are, what axes that you should choose such that when you calculate the rotational inertia tensor, it is diagonal. So if we diagonalize a moment of inertia tensor, then what it looks like is just three components, of course, on the diagonal, and these I1, I2, and I3 just represent the rotational inertia about the three different principal axes. So I1 is the rotational inertia about the first principal axis, which we said was going to be in the direction E1 hat. I2 is the rotational inertia about the second principal axis, and I3 is the rotational inertia about the third principal axis. Okay, so the process of diagonalizing this tensor involves finding the eigenvalues and eigenvectors of the matrix. We're going to represent our tensor as a square matrix. So depending on what types of courses you've done, you may have seen this already. So you often see this in quantum mechanics. I don't know if it's in the third year or the fourth year course, but you'll often express the Hamiltonian as a matrix, and you will go through a process of finding the eigenvalues and the eigenvectors of that Hamiltonian. Another place you might see this is in, maybe some kind of linear algebra course. So what do I mean by eigenvalues? Eigenvalues are going to be the elements of the diagonal matrix. So the elements that we're going to be interested in are going to be these rotational inertia about the principal axes. And what the eigenvectors are going to tell us, they're going to tell us the direction of the three principal axes. So the eigenvectors give the directions of the three principal axes. Okay, so what we'll actually spend almost all of this video doing is not so much mechanics, but we're going to just do a general discussion about matrix diagonalization. So in some sense, this is really a video about linear algebra. So don't tell your math profs, all right? So first, what we're going to do is a general discussion about matrix diagonalization. Okay, so the notation that I'm going to use is I'm going to use a double underline for a square matrix. So this is a square matrix. And I'll use a single underline for a column vector. Okay, so for a square matrix T, the so-called Eigenvector equation is the following. So we want to take T, multiply it by a column vector, and what we want to get back is some constant, a scalar quantity, multiplying that original column vector. So I'm going to call this equation star. So i.e. the product square matrix T times column vector A returns the column vector A returns A scaled by a factor lambda. Lambda is an eigenvalue, and if star holds, then A would be an eigenvector. And we're going to assume that A is not the trivial case where it's just a column of zeros, right? So it has to be some kind of column vector with some non-zero entries. So we could express star in an equivalent way. So an equivalent way to express star is, so we'll leave the left-hand side alone, but I'm going to take the right-hand side and I'm going to insert the identity matrix, so the square identity matrix, where 1 is the identity matrix. So for example, if T is 3 by 3, then we would say the identity matrix in this case would just be a diagonal matrix where the diagonal entries are 1. Okay, so let's take this thing, and what we could do is we could say, well, I could write that as t minus lambda times I, all multiplying the column vector A. So I've effectively just subtracted the lambda times 1 times A and brought it over the other side, and so that would leave a column of zeros on the other side. So here, if this was a 3 by 3 case, the column vector 0 would just be a column of zeros. Okay, so fine. So if we supposed that this square matrix in the brackets here, so everything in the brackets, if we suppose that that had an inverse, if t minus lambda times the identity had an inverse, right? Not all square matrices can be inverted, but let's suppose that we could invert this square matrix, so that we'll write the inverse as the following. Then what that would allow us to do is we could take this equation above and we could multiply it by this inverse, and what it would look like is t minus lambda times the identity inverse times t minus lambda times the identity times A would be equal to t minus lambda times 1, or the identity, inverse times 0. So we just multiply both the left and right hand sides by this inverse. Well, of course, this matrix multiplied by its own inverse is just going to return the identity, and anything multiplied by a column of zeros, any square matrix multiplying a column of zeros is going to return 0. And so what we would get is that the identity times A would be equal to 0. Well, the identity's not 0, so that means the only way this is possible is if our eigenvector A is equal to 0. So this is only true if A is equal to 0. But if you go back, we assumed that A was not equal to 0. Oh, sorry, I should fix this. A is not equal to 0. Okay, so this argument says that if our eigenvector equation holds, if the eigenvector equation star is true, then it must be the case that the inverse of t minus lambda times the identity does not exist, so that this matrix does not have an inverse. So the linear algebra people have a language for this. In the language of linear algebra, algebra, they would say that t minus lambda times the identity is singular. Okay, so it has no inverse, and singular matrices have a determinant that's equal to 0. This means that the determinant of t minus lambda times the identity is equal to 0. Okay, so let's think about the 3 by 3 case. The reason we're thinking about a 3 by 3 case is because we're going to apply this to our rotational inertia tensors, which are represented by 3 by 3 matrices. Okay, so for a 3 by 3 matrix T, the determinant that we have to calculate then is T11, and then we have to do the identity times lambda. We have to subtract that off, and so the diagonal elements of the identity are 1, so we get a -1 for the first diagonal element. And then we have T12, T13, there's no off diagonal elements for the identity. And then we have a T21, and then we have another diagonal, so we subtract off a lambda. Then we have T23, T31, T32, and then our last diagonal element, we'll have to subtract off a lambda again. And so we want that to be equal to 0 if our eigenvector equation is valid. So if you take the determinant of a 3 by 3 matrix, you're going to get a cubic equation. So number sign leads to a cubic equation, which has 3 roots. These 3 roots we're going to call lambda 1, lambda 2, and lambda 3, and these are the eigenvectors. They're the eigenvalues. These roots are the eigenvalues. So when we do this for a rotational inertia tensor, the eigenvalues that we're going to find correspond to the rotational inertia about each of the principal axes. So at I1, I2, and I3. Okay, just to write it down, the most general case here for our 3 by 3 matrix, the determinant would be, so what would we have to do? The first thing we would do is we take the first element, and then we'd multiply it by this cross multiplication. And so we would get what? It would be T22 minus lambda times T33 minus lambda, and then would be minus T23, T32. If this was a rotational inertia tensor, it would be symmetric, so T23 and T32 would just be T23 squared. But in general, you don't have to have a matrix that is symmetric. Okay, and then what you would do is you would take minus the second element in the top row, and then we would do a cross multiplication like this. Okay, so we get a T12, and then we're going to have a T21, T33 minus lambda, minus T23, T31. Okay, and then the last one is we would take plus the last element in the top row, and then we would do this cross multiplication. So T21 minus lambda, T31. Oh, sorry, no, I got to do first, sorry, T21, T32 minus, and then it would be T31, T22 minus lambda. Right, there we go. Okay, good. So if you actually expanded out all of these terms, which I'm not going to do, you're going to have some terms that are like lambda cubed, some that are lambda squared, some that are linear in lambda, and some that don't involve lambda at all. And that's a cubic equation equal to 0, so there'd be 3 solutions, and those are the eigenvalues. So here's the question. So let's suppose that we actually solved the cubic. Suppose we've solved number sign, which is that determinant equation, for the eigenvalues, lambda 1, lambda 2, and lambda 3, then how do we then find the eigenvectors A1, A2, A3? So if you remember the original eigenvector equation that was star, we had T times A had to be equal to lambda times A, so we got A back with some scaling, and the scaling is the eigenvalues. So now we know them, and there's 3 of them, so there must be 3 corresponding eigenvectors, A1, A2, and A3. So how do we find those is the next problem. Okay, so I want to go back and let's just look at equation star here. So there it is, equation star. So we're going to return to star, and we're just going to take one of the eigenvalues, say lambda 1, and we're going to insert into that equation. So let's do that. Okay, so we return to star and sub in, say, lambda 1. Okay, so in general, we have this 3 by 3 matrix where, you know, all of these elements, Tij's, we know their values. It's not diagonal, right? So there's off diagonals. But we know those elements. What we don't know are the components of the eigenvectors. So we don't know a1x, a1y, or a1z. But it must satisfy this equation. So we don't know the components of A1. So specifically, we don't know A1x, A2, A1y, and A1z. So we have 3 unknowns. And what we require is 3 equations to solve for the unknowns. Okay, well, lucky for us, this matrix equation right here is a set of 3 equations. And so we have the 3 equations that we require right in front of us. So one of the equations is, let's just do the matrix multiplication. Let's do the first row and see what happens. So we would get T11 A1X plus T12 A1Y plus T13 A1Z would have to be equal to lambda 1 A1X. So the other two are similar. So that is, we get one equation from doing the first row multiplication, we get the second from the second row, and we get the third from the third row. So equation star already gives us our system of three equations. So we can solve these three equations for the components of the eigenvector A1. Okay, so what you would do then is you'd go back to star and you would swap out lambda 1 for lambda 2. And then you'd get three more equations and you'd solve for the components of lambda 2, of A2. Then you put in lambda 3 and you get three equations that you can solve for the components of A3. All right, so that's how you would do it. We're going to do an example, but first, it may not be obvious yet, why is this process called diagonalizing a matrix? So, to see why, let's do the following. Let's define a diagonal matrix D where the diagonal elements are the eigenvalues. So D is going to be equal to lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3. Okay, and suppose that we have found our eigenvectors. These eigenvectors are A1 is going to be A1x, A1y, A1z, three components, and then of course the same thing for A2. And A3. So we've done this process of, we found the determinant that resulted in a cubic equation. We found the roots of that cubic to get the three eigenvalues. Then we went back to our eigenvector equation star. We subbed those eigenvalues in one at a time. We got a system of three equations in each case. We solved that system of three equations for the components of our eigenvectors. So we know all that stuff. Okay, so let's take those eigenvectors and let's use them to construct a square matrix that I'm going to call C. So let's define also a square matrix C in terms of our eigenvectors. Okay, so what does that look like? What I'm gonna make kind of a funny notation where I'm going to construct a square matrix by combining a bunch of column vectors. So I'm going to take my 3 column vectors, put them side by side, and make a square matrix so that the elements of C are the 3 components of A1, the 3 components of A2, and the 3 components of A3. So this is A2Z we still need, and then we need A3X, A3Y, A3Z. Okay, so there it is. So let's see what happens if we take our diagonal matrix D and take a product with our square matrix C. Okay, so there's just a lot of writing, okay? So it's not hard, it's just a lot of writing. So I'm going to rewrite C just to try to be as complete as possible. A2Z, A3X, A3Y, A3Z, and then the diagonal matrix is just the 3 eigenvalues. Okay, so if we actually did that multiplication, which I guess we're going to do, it's not too difficult because so many of the elements of the diagonal matrix are 0. So we would first just get a lambda 1 A1x. So we take the top row and then we multiply it by the first column. Then we take the top row and we multiply it by the second column, and we're just going to get a lambda 2 A2x. Sorry, that's not right. No. I want to do this row multiplied by the second column is correct, but I wrote down the result in the wrong place. We get a lambda 2 A2x right here. And then we take the top row and multiply by the third column, and that's going to be a lambda 3 A3x, and the result goes here, A3x. Okay, good. And then we do everything the same, but with the middle row, and we'll get lambda 1 A1y, lambda 2 A2y, lambda 3 A3y, and then we do everything the same with the bottom row, and we get a lambda 1 A1z, lambda 2 A2z, and lambda 3 A3z. Okay, good. So notice then what we've got is over here we have just lambdas, 1s. These are all lambda 2s, and these are all lambda 3s, and they're just multiplying the original eigenvectors. There's the first component of A1, the second component, and then the third component. And the same thing for the A2 and A3 cases. So using the funny little notation that I had made up before, we could write this as lambda 1 times the A1 column vector. And the second column is lambda 2 times the A2 column vector, and then lambda 3 A3. Okay. So that's C times D, the diagonal matrix. Let's now think of doing, remember our original matrix that we started with was T, and it was completely arbitrary, so it has no non-zero elements. And then let's multiply that by C, which was our matrix that was constructed out of the eigenvectors. So again, lots of writing. So here's all the elements of T, and we're being completely general here. They could all be completely independent of one another. 3, 1, 3, 2, 3, 3. Okay, and then C was constructed from the eigenvectors. A1x, A1y, A1z, A2x, A2y, A2z, A3x, A3y, A3z. Okay, and we just do the multiplication. Okay, and now this is a big mess. Okay, so this is going to be what? T11 A1x plus T12 A1y plus T13 A1z. All right. Let me do now the second row times the first column. So that would be a T21 A1x plus T22 A1y plus T23 A1z. And then let's do the third row times the first column. T31 A1x plus T32 A1y plus T33 A1z. Okay, so that's just the first column of this thing, and so there's 6 more elements to this matrix that look similar. But I think what you can do is you could confirm to yourself that really this is just the square matrix T times the eigenvector A1. So if you just went through the product of T and A1, you would get exactly the 3 elements constructing this column vector here. If we did the same thing for the second column in the matrix C, which was made from the A2 eigenvector, what you would find is that would just be T times A2. And then if you did the third column of matrix C, you would just get the matrix T times A3. Okay, so I want to compare this result to this result. What we have is for example, we have T times eigenvector A3, and over here we have eigenvalue lambda 3 times eigenvector A3. That's just exactly the requirement of our original equation star. So if it's true, if equation star is valid, and so remember what equation star was. It was T times A equals lambda A. Then what we're getting from T times C is T times A. Then it must be the case that, so it was T times C. So it must be the case that T times C is equal to what? Lambda times A. How are we getting lambda times A? We're getting lambda times A from C times the diagonal. that must be equal to C times the diagonal matrix. All right. Or if we multiply both sides by the inverse of C, sorry, no, that's not what I wanted to do. I do want to multiply by the inverse of C, but I want to do the other way. I want to solve for D, the diagonal matrix. So C inverse T times C is equal to C inverse C times D. And of course, this is just going to be D. And so therefore, D is equal to C inverse T times C. And let's remember what C was. C was constructed from our eigenvectors. So therefore, once we find the eigenvalues lambda, let's say lambda I, we can use them to determine the eigenvectors at AI. These eigenvectors can then be used to construct a matrix C that diagonalizes T. Okay, good. So that's a lot of technical linear algebra stuff. Let's just put it into practice. Let's do a simple example. We'll start with a simple example just to sort of get a sense of how all of this works. So our simple example will be a 2x2 matrix. Okay, and so we'll just make something up here where T is clearly not a diagonal matrix. So how does all of this process work? Step one is we find the eigenvalues. How do we find the eigenvalues? We take the determinant of our matrix T once we've subtracted off lambda from the diagonal elements. So this was the T minus lambda times the identity, has no inverse, and so it's singular, which means its determinant is equal to 0. Okay, so determinant of a 2x2 matrix is easy enough. 5 minus lambda times 2 minus lambda minus 3 minus 6. Okay, so we require 0 is equal to 5 times 2 is 10. And then what do we have? Minus 2 lambda minus 5 lambda. So is that a minus 7 lambda? And then minus lambda times minus lambda is plus lambda squared. And then 3 times 6 is 18. So I guess we get a minus 18. Or we have lambda squared minus 7 lambda minus 8 is equal to 0. So this is a quadratic equation. We had a 2 by 2 matrix. If we were doing 3 by 3, we'd get cubic. This isn't so bad to factor. So we've chosen numbers in a way that leads to a relatively straightforward result. We could factor this as lambda minus 8 times lambda plus 1. So the cross terms are going to be a minus 8 lambda plus 1 lambda, which is the minus 7 lambda that we want. Okay, and so that has to be equal to 0. So therefore the roots, or therefore the eigenvalues, are, if we set lambda equal to plus 8, we'll get a 0. So lambda, I'm gonna say lambda 2 is equal to plus 8, just to be consistent with my notes here. And then if we look at the other bracket, we have lambda plus 1. So if we set lambda equal to minus 1, we'd have minus 1 plus 1, which is 0. So the other root, or the other eigenvalue, is minus 1. Okay, so there are our eigenvalues. 2. Step 2 is find the eigenvectors. Let's start with lambda 1 is equal to minus 1. So we go back to star, equation star, which was our eigenvector equation, and that said, we needed to satisfy the following equation. Now I'm going to put subscripts 1 because we're going to end up with 2 eigenvectors, and so let's look for the first one. Again, we don't know the components of A1, so those are our unknowns, so we need to set up a system of 2 equations. But this matrix condition does it for us. So our original T matrix was the following, and then we don't know the components of A1, so we just have an A1x and an A1y. And then lambda 1 we've found, so we're going to get a minus for lambda 1, and A1x and A1y. Okay, so we do the matrix multiplication. We get 5A1x minus 3A1y must be equal to minus A1x. So that would be the first row multiplied by the column vector. The second row would be a minus 6A1x plus 2A1y would be minus A1y. Okay, so let's see, we have A1x on both sides, so let's add A1x. Add A1x, and so we get 6A1x minus 3A1y is equal to 0. Suppose we divided by 3, we would get 2A1x minus A1y is equal to 0. Okay, for the second equation, we have A1y on both sides, so we would get minus 6A1x, and let's add A1y plus 3A1y is equal to 0. This time, let's divide by minus 3. So we would get 2A1x minus A1y is equal to 0. And so what we find is that both of the equations lead to the same condition. Okay. So both equations lead to what A1y is equal to twice A1x. So at this point, really, the eigenvector we're just looking for a direction. So I don't necessarily care about its length. And so I'm free to choose arbitrarily one of the components. So if you think of, like in the mechanics case, what are we going to be solving for? We're going to be solving for principal axes. And so I just want to know the direction of that axis. I don't care what the length of the eigenvector necessarily is. So we're free to choose a1x arbitrarily, for example. Arbitrary, I don't know how to spell that. Arbitrarily. So let's just say we set a1x equal to some c. Okay, so then that means that a1y is equal to 2c, and we would therefore have that a1 is equal to c times times the column vector 1, 2. This is the lambda 1 equals minus 1 case. If we go back to mechanics, what you might do is you might say, well, what I really want is the unit vector in the direction of the principal axis. And so if you want a unit vector, then you're going to require that your eigenvector have length 1. So we could, if we wish, normalize a1. And so that means that I'd want a1, let's imagine we did the following, where I'm going to use a squiggly line to say that this is a row vector. Okay, and so we could require that that be equal to 1. So if we did that, we would get c squared 1, 2 times 1, 2 would have to be equal to 1, which is c squared, let's see, 1 plus 4 is equal to 1, and so therefore c would be equal to 1 over root 5. And so our normalized eigenvector would therefore be a1 is equal to 1 over root 5 and 1, 2. And this is the lambda 1 equals minus 1 case. All right. So we should check that this actually worked. So let's check equation star, the fundamental eigenvector equation, which said that we need this to be equal to lambda 1 times our eigenvector. And so what do we get? We get 5 minus 6, and then we get minus 6 plus 4, which is 1 over root 5 minus 1 and minus 2. Let's take out the minus sign, so it's minus 1 over root 5, 1, 2, but this is just a1, and minus 1 is lambda 1, and so we get lambda 1 times a1 back. All right, success. Okay, that was one of the eigenvectors. Let's do the lambda 2 equals 8 case. So it's just the same process. where we have now the unknown components of vector A2. And our eigenvalue is 8. Okay, so what do we get? 5a2x minus 3a2y is equal to 8a2x. What would be the best thing to do? Let's take the minus signs over to the right-hand side. So then we would get 8 minus 5 would be 3a2x, and then we'd add 3a2y. That would have to be 0. Or what we get really is that a2x is equal to minus a2y. Okay, and then the second equation, if we work with the second row of our T matrix, is minus 6a2x plus 2a2y is equal to 8a2y. Okay, so we get 6a2y plus 6a2x is equal to 0. And again, we get the same thing. We get a2x must be the negative of a2y. So once again, we got the same condition from our two equations. So we have a freedom of choice to make again. So let's select a2x is equal to c, so that a2y is equal to minus c, and therefore a2 is equal to c 1 minus 1. If you wanted to normalize, you could confirm that if you did normalization, then a2 would be 1 over root 2, 1 minus 1. Okay, so if you took, say, the dot product of a2 with itself, you'd get 1 over root 2 squared. So you'd get 1/2, and then you get 1 plus minus 1 squared, which would be 2. 2 divided by 1/2 is 1. Okay. We should do this check again. So we're going to check that TA2 equals lambda 2 A2. So T is 5 minus 6 minus 3, 2. And then A2 has, well, okay, it has a 1 over root 2, right? And then it's 1 minus 1. So that's 1 over root 2. 5 plus 3. So there's our 8. And then we have minus 6 minus 2. There's our minus 8. And so this is equal to 8 times 1 over root 2, 1 minus 1. And this is lambda 2, and this is A2. So again, that worked out nicely. All right, so I think the last thing I'm going to do in this video is we claimed that what we could do is construct a matrix C out of our eigenvectors, and then from those we could make a diagonal matrix that should have elements that are equal to the two eigenvectors. So the last thing we'll do is we'll verify that D is equal to C inverse T times C, where C, remember, was made from, oh crap, I did that again, made from our eigenvectors, A2 and A1, or A1 and A2, I guess. So let's see, we have to go back and we have to figure out what was A1. A1 was 1 over root 5, 1 and 2. So it's 1 over root 5, and I guess it's, oh, sorry, 1 over root 5, right? And then it's 2 over root 5, I think. Okay, and now A2 was 1 over root 2 and minus 1 over root 2. Root 2 and minus 1 over root 2. Okay, so what we have to do is we have to find the inverse of this matrix. So we need C inverse. And so some of you might remember how you could invert a 2 by 2 matrix. So this only works for 2 by 2. The first thing you do is you divide by the determinant of C. And then what you're going to do is you're going to swap the first diagonal elements. Okay, so let's do that swap so that you have a minus 1 over root 2, and you're going to end up with a 1 over root 5 over here. And then what you do is you take the negative of the other diagonal elements, but you leave them in their original positions. You just put in a negative sign. So we get minus 1 over root 2, and we should end up with a 2 root 5 with a minus sign. Okay, good. So what's the determinant of C? That is going to be 1 over root 5 times 1 over root 2 with a minus sign minus 1 over root 2 times 2 over root 5. So root 2 times root 5 is root 10. So I guess we get minus 1 over root 10 minus 2 over root 10, which is minus 3 over root 10. Okay, so then hopefully C inverse, so we take 1 over the determinant, it's root 10, with, there's a minus sign, and we get a 3, and it's minus 1 over root 2, minus 1 over root 2, minus 2 over root 5, and root 5. We could maybe clean this up by taking the root 10 inside, minus 1/3, and so root 10 divided by root 2, I guess, is root 5, and so we get root 5, and then we have 2 root 2, and then we have a root 2. Oh. Let's do one more thing. Let's just bring the negative sign inside. I should have done that in one step. So if we've done this correctly, And I'm doing something a bit different than what's in my notes, so it's a gamble. Root 5, 2 root 2 minus root 2. So before we go on, let's just make sure that if we actually calculate C times C inverse, that we get the identity back. So let's verify that C inverse is equal to the identity. So C was root 5, root 2, 2 root 5. Okay, so 1 over root 5, 1 over root 2. I think, was it 2 over root 5, and then minus 1 over root 2? Let's just go check. Let's make sure. I think that's probably right. We're going to get a 1/3 from the C inverse, and then we'll have a root 5, 2 root 2 minus root 2. So this is C times C inverse. So we get 1/3. Okay, so we have a root 5 times 1 over root 5 is a 1. And then we have 2 root 2 divided by root 2 plus, okay, so that's good. That's a good start. Then we get a 1, so from the root 5 divided by root 5, and then we get negative root 2 divided by root 2, so minus, okay, that's good. And then 2 root 5 over root 5, so we get a 2. And then we get a minus 2, so that's good. And then we get 2, and we get a plus 1. Okay, good. So that's equal to 3 divided by 3, and then 0, 0, and 3 divided by 3. Okay, good. So now we have C and C inverse. So what we were going to try to show was that the diagonal matrix should be equal to C inverse T times C. So we start with C inverse, 1/3, and it is root 5, 2 root 2 minus root 2. And then T was 5 minus 3 minus 6, 2. And then C was 1 over root 5. Oh, 1 over root 5, 1 over root 2, 2 over root 5 minus 1 over root 2. Okay, so let's hold our breath and let's do this. 1/3. So I'm just going to write out I'll do the product of the second two matrices first. So we get 5 over root 5 minus 6 over root 5. And then we get 5 over root 2 plus 3 over root 2. Then we get minus 6 over root 5 plus 4 over root 5. And then we get minus 6 over root 2 minus 2 over root 2. So it's 1/3 root 5, 2 root 2 minus root 2. And so 1 over root 5 minus 1 over root 5, and then 8 over root 2, and minus 2 over root 5, and then minus 8 over root 2. So it's 1/3 of, okay, minus 1, minus 2. And then we get 8 root 5 over root 2 minus 8 root 5 over root 2. Okay, so that's encouraging. Then we get a minus 2 root 2 over root 5, and then we get a plus 2 over root 2 root 5. Good. So this one we can see is 0, and this one we can see is 0. And so let's just hope that this last one works out. So it's 16, okay, plus 8, did that work? 16 plus 8, yeah, I think so. Okay, good. So that's equal to 1/3. We get minus 3, 0, 0. 16 plus 8 is 24. Take in the 1/3, and so we get minus 1, 0, 0, 8, and that was, minus 1 was our first eigenvalue, and 8 was our second eigenvalue. Okay, good. So there's all the properties of matrix diagonalization. Usually, I mean, at least for what we're going to do, we wouldn't do this last bit where we construct the matrix C, take its inverse, and then calculate the diagonal, right? We're going to be satisfied with finding the eigenvalues and finding the eigenvectors and possibly normalizing those eigenvectors. That's what's going to have physical meaning when we're talking about like a rotational inertia tensor or something like that. All right, very good. Thanks very much. And I liked the new software, so if you liked it, let me know by leaving a comment. All right, till next time.